Hey everyone, welcome back to the Deep Dive. You know we love to keep you up to date with what's happening in machine learning research, and today we're going to be diving into something pretty cool: image restoration.
Yeah, specifically a paper looking at a new way to handle image restoration, especially when images are messed up in multiple ways, which, let's face it, is how most real-world photos are.
Right, like you take a photo, it's maybe a little blurry, there's some noise, and then you upload it and it gets compressed. It's never just one thing.
Exactly. And the paper we're looking at today tackles this challenge with a pretty clever multi-agent system. It's called, well, multi-agent image restoration.
Catchy, huh? But before we get into the nuts and bolts of how this system works, I think it would be helpful to give everyone some context on the problem itself and how it's been approached in the past.
Absolutely. So image restoration, at its core, is all about trying to undo the various degradations that can happen to an image, whether that's noise, blur, low resolution, or compression artifacts.
And for a long time, the dominant approach was to develop very specialized models.
Yeah, you'd have one model that was really good at removing noise, another one for deblurring, another one for dealing with haze, and so on.
Like a toolbox full of specialized tools?
Precisely. And these specialized models can work incredibly well, but only if you know exactly what type of degradation you're dealing with.
And in the real world, that's rarely the case.
Right. So then researchers started developing these all-in-one models, trying to create a single neural network that could handle multiple types of degradation simultaneously.
Makes sense. But are those effective?
Well, they can be, but they're incredibly difficult to train, and they often struggle to generalize well. If they encounter a type of degradation they haven't seen a lot of during training, they tend to perform poorly.
So they're kind of like a jack of all trades, master of none?
Sort of, yeah. And that's where the idea of using agents for image restoration started to emerge.
Okay, now we're getting to the good stuff.
Right. So earlier attempts like Restore Agent and Edge and AIR used LLMs to try to figure out the optimal sequence of pre-trained tools to apply to a given image.
So the agent would analyze the image, decide what kind of problems it has, and then say, okay, I need to use this denoising tool first, then this deblurring tool, and so on.
Exactly. But those early attempts had some major limitations, particularly with efficiency. The process of searching for the optimal sequence of tools could take a really long time, even for small images.
The paper actually mentions that Agentity-Tor could take up to 200 seconds and 20 GPU invocations for a relatively small image.
Yeah, that's not exactly practical.
Not at all. And the paper also suggests that relying on a single agent to handle all aspects of the restoration might not be the most effective approach.
Right. One agent trying to be an expert in everything might not make the best decisions for each specific problem.
Which brings us to the paper's proposed solution, MAIR, the multi-agent image restoration system.
Right. And MAIR introduces several key innovations to address those limitations of earlier agent-based approaches.
So let's dig into those innovations. What's the first big idea they bring to the table?
Well, the first thing they do is introduce what they call a real-world degradation prior. Basically, they analyzed how images tend to get degraded in the real world and found that it often happens in a specific sequence.
Oh, so it's not just random, there's a pattern.
Exactly. They found that most real-world degradation processes can be categorized into three main stages: scene degradation, imaging degradation, and compression degradation.
Okay, let's break those down. What falls under scene degradation?
Scene degradation refers to things that are inherent to the environment when the photo was taken, like if it was raining, hazy, or had poor lighting conditions.
And then imaging degradation would be what? Problems caused by the camera itself?
Yeah, like noise from the sensor, blur if the camera moved, or low resolution if you zoomed in too much.
And compression degradation is pretty self-explanatory. It's the artifacts that come from saving or sharing the image in a compressed format like JPEG.
Right. So MAIR is built on this understanding that degradations often happen in this sequence: scene, imaging, and then compression.
And because they know this order, they can use it to their advantage.
Exactly. They propose a three-stage restoration framework that essentially reverses this process.
So first it removes the compression artifacts, then fixes the imaging degradations, and finally tackles the scene level problems.
Right. And the paper provides strong evidence that this approach makes sense. They analyzed a huge number of different restoration plans and found that the most effective ones almost always followed this three-stage structure.
So it's not just a theory, it's backed up by data.
Right. And this structured approach also makes the system much more efficient because it significantly narrows down the search space for possible solutions.
It's like having a map instead of wandering around aimlessly.
Precisely. But the three-stage framework is just one part of the story. The real magic of MAIR lies in its two-level multi-agent system.
Okay, tell me more about that.
So at the top level, you have the scheduler agent.
And what does the scheduler do?
The scheduler is responsible for getting a general sense of the types of degradation present in the image. It uses a visual assessment model called depict QA to get a first look at what's wrong with the picture.
So depict QA is like the system's eyes.
Kinda, yeah. It gives the scheduler a general overview of the problems. Then, the scheduler uses GPT-4o, a large language model, to formulate an overall three-stage restoration plan.
So it figures out the high-level strategy based on what depict QA tells it.
Exactly. And it can also take into account any specific instructions from the user. Like, if you wanted to remove the noise but keep the image blurry for artistic reasons, you could tell the scheduler that.
Interesting. And does the scheduler just come up with this plan from scratch every time?
No, actually, it learns from experience. It remembers what sequences of tools have been successful in similar situations.
So it gets smarter over time.
Exactly. But there's another interesting challenge that the scheduler has to deal with. Even within one stage, there might be multiple problems to address, and the best order to fix them isn't always obvious.
Like, if an image is both noisy and blurry, should you remove the noise first and then deblur, or the other way around?
Precisely. To figure this out, the scheduler looks back at its history of successful tool applications and uses GPT-4o to analyze those past successes and identify effective intra-stage orderings.
Clever. So the scheduler figures out the big picture plan, taking into account the 3 stages of degradation and any special instructions from the user. Then what happens?
Then the action moves to the second level of the system, where we have a team of specialized expert agents.
Okay, this is where the multi-agent part really comes into play.
Right. Each expert agent is responsible for handling a specific type of degradation. You have a JPEG expert for removing compression artifacts, a deblur expert for fixing blur, a DN expert, and so on.
So it's like a team of specialists, each with their own area of expertise.
Exactly. And when it's their turn, as dictated by the scheduler's plan, each expert does a more fine-grained assessment of the specific degradation they're responsible for. They also use depict QA for this, but in a more targeted way.
So depict QA is used both by the scheduler to get a general overview and by the experts to look more closely at specific problems.
Right, and then comes another really cool part.
Yeah.
The expert agents use a tool registry to select the most appropriate tool for the task at hand.
Okay, what is this tool registry?
It's basically a database of pre-trained image restoration models, which they call tools, along with detailed descriptions of what each tool does, when it's most effective, how efficient it is, and any potential downsides.
So it's like a catalog of specialized skills.
Exactly. The expert agents use this information, along with their own analysis of the image and the user's instructions, to choose the best tool for the job.
This is smart because it means they don't have to constantly retrain the system for every new tool that comes out.
Right. And once an expert agent has applied a tool, it reflects on the result to see if it's good enough. If not, it might try a different tool from the registry.
It's like they're iterating and refining their approach until they get it right.
Exactly. And this whole process repeats until all 3 stages of the restoration plan have been executed.
And the results, as you mentioned earlier, are quite impressive.
Yeah, MAIR consistently outperformed existing methods, both in terms of image quality and efficiency. They showed significant reductions in processing time and the number of tool invocations compared to earlier agent-based approaches.
So it's not just better, it's also faster and more efficient.
Right. They also did a bunch of ablation studies to really tease apart the contributions of each part of the system, and they found that the 3-stage framework, the intelligent tool selection, the multi-agent architecture, and the use of experience all played a crucial role in its success.
And they also showed that MAIR is very flexible. You can easily add new tools to the registry, and it's good at following specific user instructions.
Exactly. So overall, it's a really promising step forward in image restoration research.
Absolutely. So now that we've covered the main contributions of the paper, let's move on to our Novel Notions segment, where we speculate about some interesting directions for future research.
Sounds good. One thing that really stood out to me is that the current system has a fixed set of expert agents. Each agent is assigned a specific type of degradation to handle.
Yeah, that makes sense given the 3-stage framework.
Right. But I wonder if it might be beneficial to make the system more dynamic. What if the scheduler, after its initial assessment, could dynamically create or activate expert agents based on the specific needs of the image?
So instead of always having all the experts on standby, you could just call in the ones you need.
Exactly. Like if the image doesn't have any compression artifacts, you would need to activate the JPEG expert.
That would save some computational resources.
Right. And I also wonder if there could be a mechanism for task reallocation. What if an expert agent gets stuck and can't effectively address a particular problem?
Like if the denoise expert is struggling with a really complex type of noise.
Yeah. Maybe there could be a meta agent or a higher level controller that could step in and reassign the task to a different expert, or even temporarily give it access to tools from another expert's registry.
It's like bringing in a consultant for a second opinion.
Exactly. Of course, designing effective strategies for this kind of dynamic task allocation would be challenging, and there's a risk of introducing more overhead. But I think it's an interesting avenue to explore.
Definitely. What other novel notions do you have?
Another area I'm really curious about is the potential for using generative models in a more fundamental way. The current system uses diffBIR as a restoration tool, which has generative aspects, but I think there's room for a much deeper integration of generative models.
Okay, I'm intrigued. How would that work?
Well, imagine training a very powerful generative model on a massive data set of paired, degraded, and original images, specifically conditioning it on the types and severity of degradations present.
So it would learn how different degradations occur and how they interact with each other.
Exactly. And this generative model could then be used to refine the real-world degradation prior. Instead of just having a general understanding of the typical order of degradation types, the system could have a much more detailed and nuanced understanding of how they actually occur in practice.
And that could lead to even more effective restoration strategies.
Right. And I think this generative model could potentially go even further. It might be able to suggest or even fine-tune existing restoration tools, or perhaps even help create entirely new tools that are specifically designed for particular intermediate stages of the restoration process.
So the generative model wouldn't just be a tool itself, it would be a tool maker.
Exactly. I think that's a really exciting direction to explore.
Absolutely. Well, I think we've covered a lot of ground today. This paper on multi-agent image restoration is a really impressive piece of work. It highlights the importance of understanding real-world degradation processes, the power of multi-agent systems, and the flexibility of a well-designed tool registry.
Definitely. It's a great example of how thinking outside the traditional single model box can lead to significant advancements in image restoration.
As always, we encourage you to check out the full paper. The link is in the show notes. And we hope this deep dive has given you some food for thought and maybe even inspired some of your own novel notions.
Until next time.
See ya.